Welcome to solverfy.
Stars are often considered to be perfect black bodies, and so we're going to see what we can find out about a nearby white dwarf star called Sirius B. It's a type of star known as a white dwarf with a very high temperature, much hotter than the sun. But we're going to see what else we can determine about this star. So the black body radiation, we're going to write down a couple laws that govern black body radiation. The first one is the Stefan-Boltzmann law. What this formula relates is the flux or intensity of radiation from a black body, which is defined to be the power radiated per unit surface area, is equal to, we'll write it down for perfect black body, something called the Stefan-Boltzmann constant times T to the fourth, where the Stefan-Boltzmann constant is often considered to be a fundamental constant, but it is related to things like the Boltzmann constant and the Planck constant. So it kind of merges thermodynamics with the quantum theory. And its units are watts per meter squared, Kelvin to the fourth power. And as I mentioned, the intensity is the power radiated by the black body divided by its surface area. Okay, so for this star, if we know its temperature, we can determine its intensity. We simply put in our temperature and our Stefan-Boltzmann constant. And we may not have much feel for the number that comes out, but it will be in watts per meter squared. So the intensity of Sirius B is 1.88 times 10 to the 10th watts per meter squared. And like I said, we don't have much feel for this. So what we're going to do is we are told that the total power radiated by this star is about 10 to the 25th watts. Okay, so that's the total power, not the power per unit area. But by knowing this, and knowing that the power per unit area is the intensity, we can determine the surface area of the star. And therefore, we can determine its radius by assuming that it's a sphere with an area of 4 pi times the radius squared. That's the surface area of a sphere. Okay, so kind of just working through the algebra. We have the power and we have the intensity. So again, this is not something we probably have much feel for. Yeah, it's just a very large number. Yeah, 19. Okay. 5.319 times 10 to the 14th meter squared. Yeah, again, we don't have much feel for that, but let's figure out the radius of this star, and then we'll compare it to some known objects in our own solar system. So radius is then the square root of the area over 4 pi. And we can see that it's going to be about something of the order of 10 to the 6th meters. Yes, indeed, it is 6.51 times 10 to the 6th meters. Okay, so to get a feel for this, let's take a look at our sun. Our sun has a radius of almost 100 times that. And usually we write quantities for the sun with a little circle and a dot to represent our solar system, with our sun at the center, of course. But we see that that is about a factor of 100 more, 10 to the 8 versus 10 to the 6. So our sun is about 100 times larger. If we look at our Earth, that's another thing we can think a little bit about in terms of these white dwarfs. The radius of the Earth is about of the order of magnitude of this white dwarf. So that was kind of fun when white dwarfs were first being discovered. It was learned that they do have sizes about a small planet or terrestrial planet. Yeah, so white dwarfs are planet-sized. And that's hard to think of a gas squeezed down with a huge mass in it. It's kind of a weird state of matter. If we want to compare the power to that of the sun, so the power of Sirius B compared to the sun, the Sirius B puts out 10 to the 25th watts, and our sun puts out about 3 times 10 to the 26 watts. So white dwarf, although very hot, is not putting out that much power. So that ratio is about 1 to 30 in favor of our sun. The last thing we want to think about, so there's a second law for black bodies called the Wien's displacement law. And I have heard people pronounce that wine and Wien. I pronounce it Wien. And what it was recognized is that if you take a spectrum of a star and you look at the intensity as a function of wavelength, what you find is that there is a peak in the spectrum, and that peak is dependent on temperature, which is how you can estimate the temperature of many stars, is just by their spectral output. But the relationship is formulated more quantitatively in Wien's displacement law. Says that the peak wavelength times the temperature is equal to a constant. And it was a triumph of the black body quantum theory to calculate what this constant is in terms of, say, Planck's constant and other fundamental quantities. So knowing the temperature of Sirius B, which we found was 24,000 Kelvin, these black body laws always use the absolute. We can solve for the lambda peak wavelength. And often you can tell something about the temperature of a star just by looking at its visual color. That's not very accurate. But here we find that the peak wavelength is 1.21 times 10 to the minus 7 meters, which is about 121 nanometers. And I will point out that the visible part of the spectrum winds up ending at about 400 nanometers, a little bit less than that. So this is shorter than blue visible light, and we call that ultraviolet. You might say, well, gosh, if this star is ultraviolet, how do we see it? And you have to recognize that the spectrum is a distribution of wavelengths. So where we're observing this star is kind of in the longer wavelength tail of the distribution. And there are many wavelengths coming in at about equal intensity. So the color would look white to us, maybe whitish blue or kind of a colored white, but still a good reason to call this a white dwarf.